So how's everybody doing out there? Well, welcome to day 19 of Corona Online School, and today we're going to finish up section 6.1. So last time we had just talked about basic ways to represent fractions and some stuff like that. So today we want to talk about equivalent fractions, which is going to come in handy when we want to talk about addition and subtraction and stuff. We want to talk about ordering fractions, so that way we can tell when one's bigger or smaller than another one. So a lot of good stuff going on today with fractions. So before we get started, we won't use this right away, but I wanted to put on here just a little bit of what an equivalent fraction is. So an equivalent fraction is just a fraction that looks different, but represents the same fractional part. So what I mean by that, for an example, would be something like 1/2 and 5/10. So they don't look the same or anything like that, but they both represent 1/2. And so the cool thing is there's a nice way to actually test and see whether fractions are equivalent or not by taking this proportion. And so the idea is these two things are equal or proportional, is if you cross multiply them, that gives you an equal fraction. So the idea is, the way I usually do these is I kind of like check this and I put a question mark because I don't necessarily know they're true. And then I would just cross multiply, so we get 1 times 10 supposedly equals 2 times 5. And now I see that 10 equals 10, so that's a true statement. So that means that 1/2 and 5/10 are both equivalent fractions in this case. So again, hang on to that. We're going to use it in a little bit, but it's a good way to think about it algebraically. So right now we want to think about equivalent fractions in a graphical way using our models. So what I want you to do is follow the directions on practice 1, 2, and 3, and follow what they say. If you get stuck or have any questions or anything like that on those, let me know. But otherwise, I think you guys will be able to do good on those on your own. So at this point, pause the video, try those 3. If you get stuck, message me and let me know. And then when you're ready, let's move on to practice 4. Well, same thing. So practice 4, practice 5. So these are all just kind of number line things. So I figured I'd let you guys work on all these since we did the models last time. So work on the first 6 on your own. See how you do. If you get stuck or anything, again, let me know. And then, oh geez, there's a bunch of practice. Did I miss something? No, I just got lots of practice for you guys to work on. There's some for me to do too, so trust me. So go through all these guys. Here's where I was talking about doing the cross multiplying and stuff like that to try to check them and see what's going on. There we go. So here's finally my first example. So you guys work on the first 10 practice ones on your own. And again, if you get stuck or if there's something you don't understand, just let me know and I can make a little quick video. But I think you can handle these all on your own. So that's why I kind of skipped ahead of those. And then when you're done, come back. And then what I want to do is talk about simplest form, because that can sometimes cause people some problems. So pause the video, work on those first 10, and then come on back. All right. So in this case, simplest form is the way we want to think about fractions. So like, equivalent fraction is going to have lots of different possibilities, but usually there's one simplest form. And so that's what we want to focus on now, is how to write these guys in simplest form. So there's a couple different ways you can do simplest form. So I'll show you both of them, and then you can kind of decide how you want to do it. So in this case, our goal is, since I've got 8/12, then one way I could do this is I could say, okay, well, I noticed that 8's an even number, 12's an even number. So let me just go ahead and divide the top and the bottom both by 2 and just kind of simplify it that way. So in this case, I could divide this by 2, divide this by 2. So 8 divided by 2 gives me 4. 12 divided by 2 gives me 6. And then again, I notice, oh, well, 4 and 6 are both even. So let's do this again. So let's divide by 2, divide by 2. So that gives me a 2 on top and a 3 on the bottom. And at this point, there's no other common factors or anything. 2, can't divide into 3 or anything. So that's when we know we're done. So when there's no common factors on the top and bottom means that we can finish. And then this thing is in its simplest form. It's reduced as far as we can make it. So that's one way where you just kind of, start dividing stuff out that goes into the top, goes into the bottom. So the other way that you could do it is you can actually write like the top and the bottom in their prime power representation and kind of cancel them out that way. So like for example, for 8, I know this is 2 times 4, and 2 is a prime, and then 4 is 2 times 2, and all these guys are prime. So I could write 8 as, and I'd probably write it in this form rather than exponent form, just because I'll show you it makes life a little bit easier in the end. And then do the same thing with 12. So 2 and 6, and then 2 and 3. So in this case, we see 12 is 2 times 2 times 3. So now writing them in fraction form, in this expanded form, I get 3 2's on the top, 2 times 2 times 3 on the bottom. And then the idea is we want to cancel off anything that's common to the top and the bottom. So like in this case, I can take this 2 and this 2 and cancel them. I can take this 2 and this 2 and cancel them. And then finally, there's nothing else to cancel. So that just leaves me 2/3. So again, it's up to you. I'm not going to tell you which way to do it, because they both work. So one's not better than the other or anything like that. So whatever you feel comfortable with, whichever one you like, let me know. You just work on it and make sure you know how to do it. All right. So 2 other names for simplest form. So sometimes you'll hear in reduced form is another word that you'll see sometimes when you want to put something in simplest form or reduced form, or lowest terms is another word that you'll see sometimes as well. So write 8/12 in lowest terms, write 8/12 in reduced form. So they all mean the exact same thing. So the goal is we want to write it as simple as possible. So the main thing to remember is 2/3 and 8/12 are equivalent fractions, same as technically 4/6 is an equivalent fraction. So we've actually gotten 3, we started off with 8/12, and because of the way we simplified this, we actually made 2 other equivalent fractions to 8/12. So kind of keep that in mind. So in this case, name 2 more equivalent fractions. Well, we could just cheat and do what we did above, and we could say, well, 2/3 and 4/6. But you could also go the other way. You could actually kind of, instead of like dividing, what I could do is I could multiply the top and bottom by 2 and get 16/24. So that would be another equivalent fraction in this case. So the bottom one just says, explain how you can make infinitely many more equivalent fractions. And so that's the thing. With equivalent fractions, it never ends. There's a ton, and, just more and more and more and more of them. And so the way you can make infinitely many equivalent fractions is kind of what I did here. Like take 8/12 and just imagine multiplying the top and the bottom by some random n, where n can be our counting numbers, say for example. So our counting numbers. So in that case, we're looking at 1, 2, 3, 4. And so what we'd end up with, so this is a little cleaner, is just like 8n/12n. And so if you were to write all these out, like when n was 1, we'd get 8/12. When n was 2, we get, whoops, let me rewrite that because that's ugly. 16/24. If n were 3, we get 24/36. If n were 4, we'd get 32/48. If n were 5, we'd get 40/60. And you could just keep going, because the counting numbers go on and on and on and on forever. That means we can keep writing equivalent fractions forever and ever and ever and ever and ever. So don't try. It'll take you a lifetime, so there's no point in even trying. But all right, does that make sense for simplest form? All right, very good. So with that in mind, here's a bunch for you guys to try. So again, use whatever method you want. So if you want to just divide a little bit at a time as you go along, if you want to kind of factor them out first and cancel them that way, either way, you'll totally get the right answer. So that's good for me. So comparing fractions, this is going to be important because like when we're on a number line, we want to know exactly where numbers relate to each other. So the first one I kind of let you guys do on your own. So compare 3 over 1 and 1 over 3. And I think you'll know, whether they're equal to each other, less than or greater than, and then just explain your answer. But I wanted to do a couple of these just to kind of get you motivated and kind of thinking about patterns. So there's a couple patterns that we're going to be working on for these guys. So in this case, comparing fractions, illustrate each fraction with a model, then determine the correct symbol, less than, greater than, or equal to, explain your thinking. So with this one, the key to this guy is noticing that we've got the exact same denominator in this case. So we've got 2/9 over 7/9. So that's going to make a big difference. So when I'm doing the model, the one I like to do for this kind of stuff is the fraction strips, just because that gives me a better way of comparing them. So in this case, what I want to start off by doing is drawing two rectangles. And so since both of these have denominator 9, then that means I need to break this up into 9 chunks. So that means I need 8 lines in this case to do that. So I'll get 1, 2, 3, 4, 5, 6, 7, 8. And again, in a perfect world, these are all even, which obviously mine aren't even close, but whatever. So now when you do this one though, you want to try to, even though my original ones weren't lined up, you want to line these up. Just so that way when you're comparing these oddball sizes, at least they match up lengthwise and stuff. So, all right, so let me color in 2/9 first. And so I'm going to use orange for this guy. And then for 7/9, let's use blue, say. So in this case, 1, 2, 3, 4, 5, 6, 7. There we go. So there's my 2/9. There's my 7/9. And so which one do you think is bigger? Well, clearly it looks like 7/9 is much, much bigger than 2/9 because it's got a lot more squares. And the fact that they were the same denominator made it easy to kind of judge these guys because we didn't have to do anything special. We just drew the rectangles and we were done. So in reality, whenever the denominators are the same, like this case, you really don't even care about the denominators. Honestly, all you're looking at is the numerators, and the numerators are going to determine whether it's less than or greater than. The denominator is just kind of coming along for the ride. So even though this is a fraction, we really only had to look at the 2 and the 7 to decide which one was going to be smaller or bigger. So that's one of the cool things about if you've got the denominators are exactly the same. So if the denominators are the same, then we are really just comparing the numerators to see what is less than or greater than. So that's kind of a cool thing because even though we're trying to compare fractions, if they have the same denominator, really we're just comparing integers in this case and trying to figure out whether the integers are less than or equal to each other. So that's a nice thing to remember. And I guess if you forget that rule, don't worry about it. You can always sketch it out and draw it just like I did. So just kind of keep that in mind. All right, so let's look at example 3. So this is kind of the flip of the last one. So instead of having the same denominator, in this case we've got the same numerator. So let's see what happens in this case. And so again, we want to model it with a fraction. So this one's going to be a little bit different because they don't have the same denominator, but that doesn't mean we still can't compare them. So again, we want to start off with our rectangles that are the same length. And so our top rectangle, since it has a denominator of 5, that means we need to break this up into 5 chunks. So that means we need 4 lines. So like that. And then our denominator for the second one is 9. So again, we want to break that one up just like we did above into 9 chunks. So I need 8 lines. So 1, 2, 3, 4, 5, 6, 7, 8. And again, this would be better if I had graph paper or I measured them or something like that. But you'll see, like, it'll be pretty obvious again what the answer is when we sketch it out. So just like before, I'm going to let the top one be orange. So let me shade orange. So that's going to be 4/5. And let me use blue again for 4/9. And so again, even though my scale isn't exactly right, I mean, it's pretty clear that 4/9 lives inside of 4/5. So 4/9 is going to be a lot smaller than 4/5. So in this case, 4/5 is greater than 5/9. And so notice there's an actual, and this is actually going to be true in general too. So if the numerators are the same, then you only need to look at the denominators to see is bigger or smaller. But it's the opposite of like what you would normally do. Like above, 2 was smaller than 7, so we put the, made 2 less than 7. In this case, 5 is technically smaller than 9, but as a fraction, 1/5 is bigger than 1/9. So it's just the opposite in this case. So the smaller denominator, so the smaller number in the denominator is going to be bigger in this case. So in the first case, it's just like you would imagine. You get, oh, why is this thing not scrolling? Hold on, let me see. Oh, what's this thing doing? Hold on. Technical difficulties here. Let's see if restarting it helps. There we go. So in this case, like, even though the 5's smaller than the 9, since it's in the denominator, it'll actually make for a bigger fraction. So again, and if you forget, you don't have to remember these rules. You can just draw it out like I did and get the answer that way. So you don't have to memorize anything or try to remember anything. All right. So example 4 is kind of your typical example you would expect. So in this case, we don't have common numerators, we don't have common denominators. So this is really the normal type of thing that we would expect to get when we're trying to calculate fractions and compare whether they have the same denominator or not. All right, so in this case, what we want to do is do it 2 different ways. So we want to compare them without using common denominators, and then we want to compare them using common denominators. So again, we can use our set model for this just like we did before. So in this case, whoops, my iPad is not my friend today. So let's take and draw our 2 rectangles. And so again, we want to sketch 5/6 in the first rectangle. So our denominator is 6, so that means we need 6 chunks or 5 lines. So 1, 2, 3, 4, 5. And then in the bottom, our denominator is 8. So we need 8 chunks or 7 lines. So in this case, we'll get 1, 2, 3, 4, 5, 6, 7. And so again, let me use orange for the top one. And then blue for the bottom one. And so again, even though my scale is slightly off, it's not terrible. Again, I can see pretty easily just by looking at these fraction strips that 3 over 8 is a lot smaller than 5 over 6. So in this case, 5/6 is greater than 3/8. And there's no shortcut. Like we can't just look at this and say, oh, this one's always going to be greater like we could on the first two examples. So this one we really have to do something. So we either have to write them as equivalent fractions, we have to draw a model, something like that. There's no shortcut to do these kind of examples or anything like that. So, all right. So how can we compare them using common denominators? Well, what we could do is actually start off like what we did with this model as well. So like if I started off with, let's see if I can draw this the right way. 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Oh, hold on. Drew too many lines. It's gonna be one of these days. So 1, 2, 3, 4, 5. All right. And then down at the bottom. 1, 2, 3, 4. Oh, I was drawing the same 5 again. Sorry. 2, 3, 4, 5, 6, 7. All right. And so again, let me just shade these in real quick. There's my 5, 6. There's my 3/8. And so what we could do is we could try to subdivide this rectangle some more to see if we could actually get some number that's actually in common with these guys. So that way, like all the blocks ended up being exactly the same length. And then once they're exactly the same length, then we could actually just count the blocks and go from there. So like, for example, this 5, 6, I could kind of take this guy and break it up that way. And so now instead of being 5, 6, now I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 colored in. And then I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 on the bottom. And then if I went and did this, then I could actually get, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 20 on the top and 24 on the bottom. So I basically just kind of taken this and drawing the equivalent fractions that would actually go along with this guy. So now let's try to do the same thing for the 3/8 in this case. So if I did, let's see, so in this case I'm going to have to do it kind of this way. So let me draw 2 lines down the middle, so that way it kind of breaks this guy up. So originally this was 3 over 8, but now I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So my top number is 9. And then how many blocks do I have total? 1, 2, 3, 4, 5, 6, 7, 8. And then 8 times 3 would give me 24. So now that I've got them that way, I've got the same denominator. So again, my rule applies above. If you happen to remember example 2's rule, we really only have to look at the denominator or the numerators. And so I can see that 9 is much, much smaller than 20, or 20 is bigger than 9. So that would tell me that my original 5 over 6 is greater than my original 3 over 8. So again, that's how we can use our common denominator as a way. So basically just start off with your same model and start subdividing it in a way so that way you can get a common denominator. And then if you notice, if this was drawn better, like all these little squares would actually be exactly the same, unit width and everything. So mine's not the greatest, but you can tell they're pretty similar. All right, so you guys practice 13, 14, 15's a bunch here, lots of practice. 16, 17, 18. So a bunch more for you guys to practice in terms of ordering and things like that. So again, let me know if you get stuck or if you have any questions on anything. Otherwise, have a good day. I'll see you guys tomorrow. So good luck.